Welcome back to Insights Engineered with me, Ethan Simon, Global R&D Director at Laird Performance Materials, a DuPont business. Laird enables and protects the sensitive electronic components that power the world's most sophisticated devices and machines. In this series, we speak with our brightest minds who are developing novel solutions to mitigate electromagnetic interference and thermal issues in high-powered electronics. Today, I'm delighted to be joined by two key experts in aerospace and defense, Rick Johnson and John Donovan. In this discussion, we'll focus on materials that mitigate electromagnetic interference in aerospace and defense applications, and the crucial role they play in ensuring the very reliable operation of advanced military equipment, and the challenge they must operate under in very harsh environments.
The problem is there's so many different conditions, so many different operations that are done. So temperature, big thing, very high temps to very low temps. Corrosion is a huge issue, specifically with the Navy, but really with all services. And then there's other areas like fuel resistance, for example, which is a big thing for both Navy, well, for all vehicles. And then things like mechanical, problems. I mean, tremendous vibrations these things undergo. We get involved with things that even have hydrostatic pressure issues. So when you're going to the bottom of the ocean, some of the pressures can build up to 1,000 psi. So just a wide variety of different environments.
It's great. It's really interesting. And John, what sort of issues are you hearing the most about from customers today?
Yeah, so we've been working with a number of our military customers on varying challenges. One of them right now is going to be that kind of corrosion that Rick hit on. So we do have a galvanic compatibility chart that we have in our catalogs. When speccing in different types of materials, whether that be metals or gasketing, making sure that we're providing that type of corrosion resistance to our products that will make sure that they will last the test of time over the course of the years throughout the application, especially for those environmental challenges.
So Rick, back to you. Our team in Carlsbad, California designs and manufactures materials that mitigate electromagnetic interference and improve signal integrity. Things like microwave absorbers, electrically conductive elastomers, and so forth. Could you just explain the role these key materials play in A&D?
The absorbers are used in a number of applications, ranging from survivability to enhanced antenna performance and then to high-frequency EMI. Usually when EMI gets above 2 gigahertz, you need a microwave absorber solution. But to be clear, it's controlling gaps in where energy can leak out is some of the key things. So that can be with an absorber or with an electrically conductive elastomer. So if you have a gap, you want to plug that gap to minimize any areas where energy can either leak out or leak in. So that is really what we do. And because of that, a lot of these applications are on the outside of a vehicle. For example, a flush-mounted antenna on the side of a fuselage is going to get scattering in there. So you put the absorber on the outside. So one of the things about our materials is, rather than inside of a box like typical shielding solutions are, some of the absorber and ECE applications are on the outside of the vehicle.
So for some of these EMI issues that we're seeing, what we've done is do some of our MFS solutions, our multiple functioning solutions, where we have a board level shield combined with either a thermal material or an absorber. Right now we're working on a space grade application with one of our customers going into a low Earth orbiting device where we're integrating a board level shield with an absorber and making sure that it's going to be functioning properly within that device. And one of the other things too, as we're getting smaller and smaller packages and sizing, and the power has just been increasing and things are decreasing in size, there are thermal issues that we're seeing right now in the market space. We've seen a lot of different silicone requirements and silicone bleeds, so we've gone away from the silicones, and we're able to drive our thermal conductivity up to a 10 to 34 watts per meter Kelvin with silicone-free materials.
So Rick, obviously these materials are needed wherever there's communications, and those communication applications can vary from on a ship to an airplane or even a mobile structure. What are some of the challenges in airborne communications that we need to address?
Okay, so with airplanes, certainly a temperature extreme. And so we're looking at higher temperature elastomers and temperatures that are good at low temperatures as well. So some of these applications, they go down to minus 100 degrees. The adhesion of these materials onto a vehicle, that's always a big challenge. But above and beyond that, even areas like behind the nose radar, you'll get a lot of backscatter. And so in those cases, you need like a broadband foam type absorber, and then protecting a foam absorber inside that environment is also challenging. I'll go on to ships. I mean, because ships are a tremendous issue. You've got, upwards of 100 transmitters or receivers operating at different frequencies, but similar frequencies. And so, for example, you'll have a high-powered jammer, next to a relatively sensitive ECM receiver. And in those cases, we can construct barriers, absorbing barriers between the two to minimize that energy back and forth. And we do a lot of that. And so we can make broadband barriers or frequency-specific barriers to target those problems. And then another area that we do a lot in is mobile shelter. So you'll have these mobile shelters that will be taking communication equipment, maybe antennas, other types of devices, and those need to be sealed off so they're not easily detected. And so we do a lot of work for conductive gasketing for those types of applications.
So what can be done to harden these materials and make them withstand extreme environmental conditions effectively?
So maybe you can harden, but a lot of it is material selection. So we do have a wide variety of materials we can choose from. And for example, we use a lot of fluorosilicone. Fluorosilicone is basically a fuel-resistant version of silicones. And so for military applications where you're worried about fuel, hydraulic fluids, oils, de-icing, those are all things that need to be tested and verified against. So a lot of it is selection for both temperature and fuel resistance, and then the selection of fillers to minimize corrosion. And so there are standard fillers are magnetic particles that are subject to corrosion, but we can design and pick other alloys that are much more corrosion resistant.
The challenges are obviously never straightforward. Tell me about some of the more complex challenges that you've had to face recently, and maybe how you went about solving them. I always love to hear the war stories. No pun intended here. Yeah.
I'll give you a good example. Was one that it was a hatch on the outside of a vehicle that goes extremely fast. And so the problem was it had external air pressure trying to get into the hatch and internal air pressure trying to get out of the hatch. It was around 10 psi on both sides. So we had to design a gasket that would seal in both directions. Normally you just worry about sealing in one direction, but in this case you had both. It also required high temperature, fluorosilicone, also required combining an absorber with an ECE. And so we co-molded absorber and ECE together, and it was relatively large. It was over 100 inches in length and circumference. And the thing was, it was design 43. So it just tells you how many iterations that we did using Abacus FEA software and working with our customer to come up with this. And then we went through a full qualification on it. We had to, verify that it's sealed. So we came up with a little test prototype that we could inject air into, and as well as outside air, and pull vacuum on to verify this. So that was a good one. That was a success with our customer, who was said it was one of the best projects they had.
So right now we're working on a board level shield combined with an absorber. So we've taken the absorber out and we're just kind of modeling right now the board level shield. So because this is being sent up into space, there's a pressure differential and then these other forces that are being exerted. So working with the customer and their design team and modeling, they gave us the exact type of pressure differential and the forces that we'll see once it's placed onto the printed circuit board. So I was able to go back to the design team, give them the parameters that they needed in order to test. They modeled it, and then we ended up revising the board level shield. And this is, keep in mind, one of our standard board level shields, and then kind of using that as a base and then turning it into a custom part for them. So we were able to close up some of those gaps and apertures that are on the board level shield, so that way their shielding effectiveness could be exactly what they need it to be, and to go ahead and make sure that it would be able to withstand the different types of pressures.
So if you were working with a partner at a customer and you want to give them some advice about what they should look at early on in a design, which conditions are most difficult to design to? Is it corrosion, high pressure, vacuum?
I do think it's not a one-size-fits-all question. For example, Navy guys, probably corrosion. Air Force guys could be temperature or could be fuel resistance. So those are kind of the things. One of the things we're seeing is the need for lower and higher frequency solutions. And so we're developing a variety of materials, and we're looking at, particle alloys, new ones, particle shape, annealing conditions to change the magnetic properties of these materials, and then how to process those. So we're doing a lot of work trying to develop better low frequency materials, from very low in the hundreds of megahertz up to, this kind of 800 to 2 gigahertz range. On the other side, we know 5G is operating up, at higher frequencies. We know a lot of the SATCOM is 40 gigahertz. And there's still our weapon systems that have issues at millimeter wave. So the magnetic materials, lose their permeability at high frequencies. And so now we look at other novel materials. Maybe it's nanoparticles, maybe it's just lossy ceramics to achieve what we need at high frequencies. So, you can pick materials, you can pick fillers, and all of those are, helping you solve this variety of different problems.
John, what's driving some of the demand for increased thermal solutions and thermal needs?
Yeah, so some of the thermal needs are going to be coming from the smaller package sizes, as there's a giant push to make things smaller and more compact, and increasing power and the frequency of things that are going up now. There's going to be a lot of heat energy that's going to be generated. So some of our thermal products are being built right now to sustain those components, so that way there's sufficient heat transfer to those heat sinks. There's a lot of different customers out there that are having the same initiatives of making things smaller and more compact so that they have more room within the device for their uses, or whether that be other uses or just making it even more compact of a solution.
So we see increased use of drones in A&D applications. What are some of the challenges you see with next generation drones?
So drones can do a lot of things, right? They can go up and just surveil. They can maybe carry weapons. In some cases, you want the ability to just hang in the air as long as possible. In the other case, you may want it also somewhat invisible, so it can go into areas and drop weapons. So there's a lot of new applications where, they're sending them out almost like killer bees, just to overpower something, and that could be for jamming, or it could be just to decoy other things. So the new applications are really endless, and it is a big area of focus for the military.
Absolutely, yeah. So some of the drone requirements now, as they're getting more lightweight and more compact, they're also trying to fit in other things into the design. Kind of what Rick hit on earlier too, is if they're going to be carrying weapons or carrying payloads or something else, that'll free up more room for weight to be added to the system, or if they're going to go for even more lightweight and more of stealth and faster aircrafts for drones.
So as we look to the future about emerging challenges, you just mentioned the wider range of frequencies as a key challenge, and that's a really important one. And as you said, we're seeing that across the board in consumer applications, industrial applications as well. What are some of the other big challenges and emerging trends that you see as you look to design the next generation of products?
it used to be military was leading, the frequency regime into high frequencies and low frequencies. It seems like now, the commercial has kind of blown right past that, and now all the commercial devices, be it automotive radar, are operating at 77 gigahertz. So we certainly see the broad frequency range, and that is guiding a lot of the work we do in looking at the different particles. There's sixth generation aircraft. If you read Aviation Week, that's the big talk now. So, the F-35 is a fifth generation aircraft. Now they're building the next one. What is that going to be? It's going to be faster. It's going to have better communications. So all those things will drive the stuff we do.
Thanks for tuning in to this episode of Insights Engineered. Visit Laird.com or follow Laird Performance Materials on LinkedIn to learn more about our latest products and innovations as we continue to use the best of DuPont science to make the world a better and safer place.